Welcome to the video Solving Problems via Riemann Sums. In this video, we will compute areas and volumes. Our goals in this video are to first understand the concept of a Riemann sum and how it can help us approximate the solutions of various problems involving areas and volumes. Secondly, understand the general concept of the Riemann integral, regardless of its application as a limit of Riemann sums. Third, use definite integrals, which are limits of Riemann sums, and the fundamental theorem of integral calculus to calculate exact areas and volumes. And fourthly, noticing what we did in number 3, we will see how to calculate volumes of solids by integrating cross sections of that solid. Let's talk about the general concept of the Riemann integral. We'll let f be a continuous function on the closed interval from a to b and choose a positive integer n. We'll partition or divide the interval ab into n equal length subintervals. We'll let a equal x naught, which is less than or equal to x sub 1, which is less than or equal to x sub 2, all the way through x sub n, which equals b. Down here, for each I, let's pick an x sub I star in the subinterval from x sub I minus 1 to x sub I. So here's a picture of that. Here's the subinterval going from x sub I minus 1 to x sub I, and somewhere inside this interval, we pick the point x sub I star. This is a number line. X sub I star can be anywhere from equaling x sub I minus 1 to x sub I, or anywhere in between. The Riemann sum that will form for this continuous function we talked about is the nth Riemann sum is the sum I goes from 1 to n f of x sub I star times x sub I minus x sub I minus 1. The second factor is just the length of this subinterval, and this first factor here is just our value, it's our function f, excuse me, evaluated at this point x sub I star within the ith subinterval. So we're looking at this Riemann sum for a continuous function f on a closed interval ab, and we can rewrite this Riemann sum this way. Looks almost the same as what we have up here, except we have a delta x instead of x sub I minus x sub I minus 1. These are the same. Delta x is just the length of the ith subinterval. Well, since we're using equal length subintervals, each of the delta x's, each of the lengths of the subintervals is going to be b minus a divided by n. The length of the interval ab divided by n, the number of subintervals. We have the following fact. Since f is continuous on that closed interval from a to b, it turns out that the limit as n goes to infinity of s sub n exists, and this limit is a finite number. Now this seems kind of strange because I haven't told you how to pick these x sub I stars. You can pick them any way you want as long as the x sub I star is in the ith subinterval. As n goes to infinity and the lengths of the subintervals approach 0, it doesn't matter which x sub I stars you pick. You'll get the same limit, and it's some finite number. In that case, we'll define the integral of f of x dx, x going from a to b, to be the limit of these Riemann sums, s sub n's. These s sub n's, remember, we got by dividing or partitioning the interval ab into lots and lots of small subintervals, forming a Riemann sum, and we do that for each n, and as n gets larger and larger and larger, as n goes to infinity, the s sub n's that you compute will get closer and closer to some number, and that number we will call this definite integral. As I just mentioned, this is called the definite integral from x equals a to b of f of x dx. So here's a problem. Part A. Let's approximate, by lots of rectangles, the area of the region bounded above by the curve f of x equals 2 plus 1/4 the quantity x minus 4 squared, below by the x-axis, and on the left and right by the lines x equals 2 and x equals 6. So we'll do this by using a Riemann sum. Then we'll find the exact area of that region by taking the limit as the number n of rectangles goes to infinity, and then we can evaluate a definite integral to find the exact area of that region. For the approximate area under the curve, we're going to approximate it 2 times. One time with n equals 8 rectangles, like we see over here, and then to get a better, more accurate approximation of that area, we'll use 32 rectangles. And you can see here 32 rectangles. They're kind of very slim, very thin. In each of these cases, this upper curve is the same. F of x equals 2 plus 1/4 times the quantity x minus 4 squared. So what we're going to do is write down these two sums of areas of rectangles, and then we'll get a Riemann sum. In each case, I'm going to let x sub I star be the left endpoint of the ith subinterval. So if we look at this first picture here, the height of this rectangle, which is given by f of x sub 1 star, is on the left endpoint of this little subinterval going from, I guess, 2 to 2.5. So the first rectangle, we start at x equals 2, we go up till we hit the curve, go across horizontally a distance delta x, and then go down. Then for the second rectangle, we go up until we hit the curve, go across, go down, and so forth. If we have 32 rectangles, it'll be the same sort of process in that case too. So let's look at an approximation of the area under this curve, f of x equals 2 plus this stuff, and we'll estimate the area, approximate the area by looking at the sum of 8 rectangles. This sum will be a Riemann sum, it turns out. So we're going to look at the Riemann sum S sub 8 as the approximate area under that curve. So first of all, here's the definition of the Riemann sum with n terms, as we've seen before. And if we look at this, we have x sub I star here, and what we would like to do is let x sub I star be 2 plus I minus 1 times 4 over n. For instance, when I is 1, this will just be 2 plus 0 times this, which is 2. 2, x equals 2 is right here. We used x equals 2 to find the height of this first rectangle. That height is f of x sub I star, where I equals 1. So if we write out some terms here, the first term when I equals 1 is f of 2 times the length of the subinterval, which is a half because it goes from 2 to 2.5 here, plus, and then the next rectangle has height f of 2.5, and the base is still a half. And we keep going all the way through all of these rectangles to the last one, and it's going to be f of 5.5, which is the height of this last rectangle, times its base, which once again is a half. And if we add up the areas of those 8 rectangles, we get 9.375. You can try that using a calculator, for instance, or writing a little bit of computer code to evaluate this type of sum. In this, we saw that x sub 1 star is going to be this, with 1 minus 1 being 0. So you just get f of this is f of 2. And by the time you get to this last term over here, that's the 8th term, the x sub 8 star term, x sub 8 star variable is 5.5, which is right here on the x-axis, 5.5. And you're multiplying that by the base of that last eighth rectangle. And so we see how this one was found, how this one was found. All the ones in between are found similarly. That was fun. Now let's use the same technique to find the Riemann sum, the 32nd Riemann sum, using 32 rectangles here, to find approximately the area under this curve, still between x equals 2 and x equals 6. So here's our formula for the Riemann sum, which will approximate that area. And then if we want the 32nd Riemann sum, we're going to divide the interval from 2 to 6, which is of length 4, isn't it, into 32 equal length little subintervals along this x-axis. And so we'll let x sub I star be 2 plus I minus 1 times 4 32nd. The length of one of these little subintervals down here on the x-axis, since the length from 2 to 6 is 4, and we're chopping it up into 32 equal length subintervals, each subinterval has length 4 over 32. And when we calculate this sum, either by punching lots of numbers into a calculator or by maybe writing a short MATLAB program, something like that, we can find out that this Riemann sum is approximately 9.3359375. Now, this is still an approximation of the area under this curve, but it's a pretty good approximation because if you look at the sum of the areas of all these long, thin rectangles, the sum of the areas is a pretty good approximation to the area under the curve. If we want to get the exact value of the area, we'd have to let n go to infinity, and so we would be looking at the limit as n goes to infinity of the nth Riemann sum, this Riemann sum with n terms in it, and for that we can use the fundamental theorem of calculus. So let's recall the fundamental theorem of calculus. Let's let f be a continuous function on the closed interval ab. There are two parts to the fundamental theorem. Let's look at part 1, the statement of that. For any x in the closed interval ab, we'll define capital F of x to be the integral from a to x of f of t dt. So we're just integrating that little f function, that continuous function, from a to x. Notice that we have what looks like a variable upper limit on this integral, but we're doing it for any fixed number x that happens to be somewhere within that interval from a to b. So this integral, remember, is defined as a limit of Riemann sums, which is here in, I guess, light green to remind you. And the fundamental theorem of calculus says that this function capital F, when you take its derivative, is just the little f that appears in this integrand. So capital F is an antiderivative of little f. That's what part 1 tells us. If we define f of x by this limit of Riemann sums, we get an antiderivative of this integrand function. Well, that's kind of interesting. In part 2, we can say that the integral from a to b of f of x dx, f, remember, being a continuous function on the closed interval ab, that's just equal to capital F of b minus capital F of a for any antiderivative capital F of a function little f defined on the closed interval ab. Now later we might want to use a little bit of different notation for this quantity here, f of b minus f of a, capital F's. To write this in a more shorthand notation, we can say that's f of x evaluated at x equals a and b. And this would tell us to evaluate this function at b, subtract the value of this function at a. Sometimes we just leave off the x equals here because we do have the variable x here to remind us what the variable is, and we'll just have a and b here instead of x equals a and b. So this is just a shorthand notation for this sort of thing here, so we can save some lead, use our pencils a little bit longer, and we won't have to worry about inflation of pencil prices quite so much. So now we're ready to use the fundamental theorem of integral calculus to find the exact area under that curve by letting the number of rectangles go off to infinity. So remember that our function is this one that gives us this graph right here, and we're going to divide this up into n rectangles more or less and compute an nth Riemann sum. So the exact area is the limit as n goes to infinity of that nth Riemann sum, and by definition this s sub n is just the sum I goes from 1 to n of f of x sub I star times x sub I minus x sub I minus 1. And now we can use the fact that we had that fundamental theorem of calculus. So we're going to say that this limit of Riemann sums is going to be the definite integral from x equals 2 to x equals 6, which is what we have right here. The integrand is just the function that gave us this curve, 2 plus 1/4 times x minus 4 quantity squared dx. Now, an antiderivative of 2 is 2x, and an antiderivative of 1/4 x minus 4 squared is 1/12 x minus 4 cubed. You can check this yourself pretty easily by differentiating each of these two terms to see that you get this integrand up here. And we're going to evaluate this antiderivative at x equals 2 and x equals 6, and then subtract capital F of 6 minus capital F of 2. When you do that simple computation, you'll find out that this is equal to 9 1/3, which in decimal form, I guess, would be 9.3333333, and the threes keep going on until you get bored saying them. And if you compare this to the approximations that we had earlier of the area under the curve, we could see that our approximation with 32 rectangles under that curve, or they weren't actually under always, but those 32 rectangles did give us an area very close to 9 1/3. So let's consider a problem of volumes of cones, approximating the volume of a cone and using integration to get the exact value of the volume of that cone. So we'll consider circular cone with radius r equals 2 and height h equals 4. We can see that cone here in kind of a slight pink, I guess. Part A, let's approximate its volume by adding up the volumes of disks inscribed in that cone. And in this case, we're going to have one disk down here of radius 0, actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 cones, 10 disks, including a disk of radius 0 down here. So we'll do that approximation, and we'll write down what that approximation is as a sum. And then we will recognize what we did in part A as a Riemann sum involving some function and some limits for an integral. And we'll use that integral to find the exact area of that cone. So here's the picture we saw just a minute ago. And getting rid of that outline cone, we see that we have all of these disks, including a disk of radius 0, which has 0 volume down here. So looking at this cone problem, the height of the cone is 4, the radius of the cone was 2. So we'll set up the cone to go up vertically along the z-axis. And so we'll partition the interval on the z-axis 0, 4 into 10 equal length subintervals. 0 is equal to z0, it's less than or equal to z1, which is less than or equal to z2, which is all the way through less than or equal to z9, which is less than or equal to z sub 10, which equals 4. So around that ith subinterval, z sub I minus 1 to z sub I, we'll create one disk. And that disk will have radius 1/2 r sub I equals 1/2 z sub I, and the height, delta z, will be 4/10. Let's see why that's going to be the case for these two. First of all, if you look at a disk here, the radius is half the height, just as for the full cone, the radius is half the height of that cone. And so that gives us these two formulas. And then using the volume of a disk is pi r squared h, we just get pi times r squared times h. And so the volume of the cone then is going to be approximately just the sum of all of these disks. So we get the sum I goes from 1 to 10 of the v sub i's, which by this formula up here is the sum I goes from 1 to 10 pi, and here is the r squared basically, and here is the height, which is dz. One thing to notice here is that for the first cone I equals 1, we have a disk down here for the first disk. The first disk has radius 0, and so the first term here, v sub 1, happens to be 0. So if you count these disks that you actually do see here, you'll see 9, because there was a 10th here that basically had 0 for the radius. Now, if we had n disks instead of 10 disks, the only changes that we would have to make in this formula up here is to change the upper limit here, 10, to n. So we're adding up the volumes of n disks instead. And on this part right here, the radius of one of those disks, the ith disk, I going somewhere between 1 and n, is still going to be 1/2 z sub I squared, but this delta z changes. Instead of being 4/10 as it is up here, it'll be 4/n if you're using n disks. So not much of a change is necessary. So as n goes to infinity then, this Riemann sum is going to go to what integral? Well, you're subdividing the z interval, z equals 0 to z equals 10, into n equal length subintervals. So the limits on the integral are going to go from 0 to 4. And then we'll have pi, and then instead of 1/2 z sub I squared, we'll have 1/2 z squared. Instead of delta z, we'll have dz. And this is an easy calculus 1 integral to evaluate. When you evaluate it, you'll get 16/3 times pi. So the volume of the cone is 16/3 pi cubic units. If you're measuring the axes in inches, for instance, this would be 16/3 pi cubic inches. So the formula that we have looking at this is the integral from 0 to 4, and then pi times r squared is actually the area of a circle here, one of the cross sections that you would get with the cone. So it's a cross-sectional area at z dz. And as I just mentioned, we can think of A of z naught as the cross-section of the cone, and the plane z equals z naught. So what we see is, to find volumes of three-dimensional solids, we can take cross-sections of those solids by planes, and what we will get in those cases is v equals, in our particular cone case, the integral from 0 to 4, the cross-sectional area, when you take the solid, in our case a cone, and the horizontal plane z equals z naught, that would be A of z naught, but we want the z naught to go from 0 to 4 here, so we'll integrate from 0 to 4 A of z dz. This type of formula we can use to find volumes of other types of solids too. chop up the solid into lots of pieces by intersecting it with planes, and then integrate the cross sections to get the volume. So here's the general result. Put an axis through the three-dimensional solid, and for the time being we'll suppose it's the z-axis, but it could be any axis going through the solid. Suppose that the solid, the entire three-dimensional solid, lies between the planes z equals a and z equals b. And also, let's talk about cross sections. For each z0 between a and b, let a of z0 be the cross-sectional area of the solid with the plane z equals z0. So for each z0, we have a cross-sectional area. Then the volume of the solid we get by just integrating those cross-sectional areas. The volume of the solid is equal to the integral from a to b of a of z dz. So what we saw up here is that the solid is between a and b, and for each value, each z value between a and b, for instance, a z0 value, a of z0 is going to be the cross-sectional area. So down here, a of z is a cross-sectional area located at the number z on that axis. So our general formula for cross-sectional areas, volumes in terms of cross-sectional areas, is the volume is the integral from a to b, cross-sectional area a of z dz. This video concerns volumes of ellipsoids. We will use calculus techniques to find the volume inside an ellipsoid. We will see later that the equations of ellipsoids are given by equations like this: x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Let's define what an ellipsoid is. It's going to be a surface in 3 dimensions. An ellipsoid is going to be the graph of equations of this form: x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And we will consider a being greater than 0, b being greater than 0, and c being greater than 0. We can assume this without loss of generality because we just have the squares of them here. So what does an ellipsoid look like? Well, it looks kind of like a flattened or stretched sphere. We will see several examples of this very quickly. Here we have the ellipsoid x squared divided by 1 squared plus y squared divided by 2 squared plus z squared divided by 4 squared equals 1. Here's the ellipse in 3-dimensional space. This is our x-axis going from, it looks like, -7 to 7. For the y-axis, -7 to 7 perhaps, and on the z-axis, -7 to 7 also. This color scale here tells us the coordinate, the z-coordinate of a point on this surface. Let's rotate this surface around to see what's going on. If we go over this way, the extent of y values goes from -2 to 2, which matches what we have up here, y squared over 2 squared. If we rotate back this way so that we get the x-axis head on, right about there I guess, the extent of x values in the surface go from x equals -1 to 1. The z coordinates for points on the surface go from -4 to 4. So that gives us a pretty good example idea of what this ellipsoid looks like. Here we have the ellipsoid x squared over 2 squared plus y squared over 2 squared plus z squared over 4 squared equals 1. So basically in the x direction, which is along this axis, if we move this over, we can see, approximately at least, that this ellipse is somewhere between x equals -2 and x equals 2. And if we go this way to the y-axis, this ellipsoid is also between -2 and 2. And in the z direction, it goes from -4 to 4. This particular ellipsoid could be considered a volume of revolution. Here is, excuse me, here is another ellipsoid given by x squared divided by 4 squared plus y squared divided by 4 squared plus z squared divided by 2 squared equals 1. This x term and this y term both have denominators 4 squared, same denominator. Then we have 2 squared over this, under this z squared. In this case, we get an ellipsoid that looks like this, and we can see that it's not very high in the z direction, not very thick in the z direction. But if we rotate this around, if I can do it, this particular ellipsoid is also a solid of revolution, and that happened because these two coefficients of x squared and y squared were equal. Let's look at some cases involving ellipsoids. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1. If c, a, and b are all different, we have which is called the general ellipsoid, or the triaxial ellipsoid. The length of the three axes of the ellipsoid in the x direction, y direction, and z direction are all different. Suppose we look at the case where C is less than A or B, and A and B are equal. In that case, we get what's called an oblate ellipsoid of revolution, also called an oblate spheroid. In this case, C gives us basically information about the width in the z direction, and it's smaller than A and B. So the dimension, the length, or maybe the length of the axis in this direction, the z direction, is smaller than in the x and y directions. Down here, if C is greater than A, and A does equal B, then we get an ellipsoid that looks like this, that the length of this ellipsoid in the z direction is greater than in the x or y directions, and this is called a prolate ellipsoid of revolution, also called a prolate spheroid. What would happen if A, B, and C were all equal? Well, in that case, you would get a sphere. It turns out that the cross-section of an ellipsoid turns out to be an ellipse. So we first need to calculate the area of a general ellipse. So our problem is to find the area inside the ellipse x squared over a squared plus y squared over b squared equals 1. So if we start with that equation, we can solve it easily for y squared, and we get y squared is b squared times the quantity 1 minus x squared over a squared. So that means that y is then plus or minus b times the square root of 1 minus x squared over a squared. If we use the plus sign here, we get this upper curve as being y equals b times that square root. We're assuming that a and b are positive here. So what we'll do is find the area under this part of the ellipse and above the x-axis, this region here that is shaded. So half the area of the ellipse, I'll call it a over 2, is just the integral of this, which is b times the integral from minus a to a, of the square root of 1 minus x squared over a squared dx. Now, this requires a trig substitution. That's probably the easiest way to handle this. If you let u be a cosine x, then this fraction right here is going to be a square cosine square x divided by a squared. And so the stuff inside this square root becomes 1 minus the cosine squared of x, and the square root of that will give you the sine of x. I'll leave the rest of the details to you. But when you evaluate this integral, it turns out to be 1/2 times pi times a. And so half the area is b times 1/2 pi a. So the full area under the entire ellipse, top and bottom part, a is equal to pi times a times b. A is more or less half of this principal axis length. B is half of this secondary axis length. They kind of play the roles of radii in circles, but in this case we're looking at ellipses. So here's the situation that we're going to be looking at. We want to find the volume of the ellipsoid x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And the intersection of that with the plane is shown here, a horizontal plane at a particular value of c. And what happens is we get the intersection of those two surfaces being an ellipse. We will see that this intersection is an ellipse. So what we can do is to find the volume of the ellipsoid, we will integrate the areas of these cross sections from minus c up to plus c, the values that z can take on. There are different types of ellipsoids, all given by this general formula. Let's consider a, b, and c in these denominators. If a, b, and c are all different, then we have what is called the general ellipsoid, or we could call it the triaxial ellipsoid. In this case, we're going to have 3 axes for this ellipsoid, all of different lengths. If 2 of the numbers, like a and b, are equal and greater than, let's say, c, then we get what's called an oblate ellipsoid of revolution, or just an oblate spheroid. In this particular case, we can get it by revolution, and we can use our calculus techniques for finding the volumes when you sweep a region around, let's say, an axis. If you have that a and b are equal and less than c, we have what is called a proloit ellipsoid. And if all of those a, b, and c are equal, then the ellipsoid turns out to be a sphere. So we can see that ellipsoids are kind of a generalization of spheres. But in this case, they can be stretched or contracted along various directions. Thank you for watching this video. What did we do? Well, we computed the area of an ellipse. We needed that to move on to ellipsoids. Then we computed the volume of the most general type of ellipsoid. The formula that we have covers all of the cases of ellipsoids. We didn't mention it earlier, but for the prolate and oblate spheroids, those volumes can be computed by using the formulas that you had in Calculus 1 for volumes of revolution. I hope you enjoyed this slideshow, and please stay tuned for more.